So that's what I work on to date. But when I went to U of H back in 2017, so long ago, it was, I specifically did a concentration in nanosystems, and really enjoyed it. It was very materials based, so got me a really firm understanding of just the make and how a lot of these products come to market. Um, and I appreciate that and can use that moving forward. So from my perspective, coming here today, kind of just wanted to give you kind of an overview of, hey, this is who I am. And hopefully y'all have questions on some of the concentration, and this can kind of turn into a question and answer session moving forward. But that said, I did want to touch kind of generically over the nanosystems concentration. So U of H generically offers nanosystems. It's kind of more of a material science type of degree plan. If you look at other universities, a lot of other universities basically would categorize what the nanosystems concentration does under material sciences. And at least that was the case only 3 years ago. I don't assume that has changed, but maybe that has changed a little. It has a lot of focus with actual production, fabrication, whether you're going to use lithography to make your different semiconductor cards. What does the manufacturing floor look like? How clean does it have to be? What kind of uh, uh, small quantum, well, not quantum, but atomic interactions can you have between different materials? What kind of crystalline structures you can have that will work for the electronics. The nice things about the nanosystems concentration, as actually Dr. Dave put it for me, is that at the end of the day, your degree coming out of U of H is going to say electrical engineering. So you're still an electrical engineer and you graduate as an electrical engineer. It's just you have more of a background in the materials side and can apply that and understand that moving forward in your career. There's a couple different aspects that's applied. If you want to go into grad school, it's actually, I would highly recommend that with a nanosystems concentration, just because you have a very firm grasp of how a lot of these products are made. But it's very beneficial to get a little bit more electrical knowledge if you want to do an EE, or if you want to go ahead and jump into material sciences to get that material sciences depth in a master's. Or if you're going to go to the PhD route, nanosystems is actually great because there's so much research and development that you can do associated with that type of concentration area. I myself participated in an REU program, which is a research experience for undergraduates, and that was a great opportunity to get my hands into the lab environment beyond what was even just available at U of H. In fact, it's depending on which program, it's actually a little bit easier to get your hands dirty and in the lab through an REU program or a SURF program or something similar. Alternatively, like I said, if you want to go straight into industry out of a nanosystems concentration, I'd actually highly recommend looking into a bunch of foundries. They're called foundries or semiconductor fabrication centers. There's a few in the US. The closest ones are all going to be in Austin. And those are probably like Samsung, Austin. Yeah, it's basically US Samsung. I forgot, I know it's SAS, but I forgot what the acronym stands for. But there's also Micron that's out in Utah that I have actually visited, and it looks pretty cool. It's basically just a robot. The whole floor is basically just a robot. It's great. But there's a lot of, like I said, materials improvements and production improvements that you can do from that side. Yeah, so that's just kind of a general overview of kind of nanosystems, what it is, from going into research or going into industry. in kind of direct applications. I myself kind of took an indirect route. um, in that nanosystems was really great for getting us a system level understanding of, hey, this is what are the different components and what they all do. And it all depends on what classes you take at the end of the day. I took a controls class and an antennas class and then a power electronics class. So it's like that gambit of classes are so many things that all counted towards the degree that, you really kind of apply different aspects of it throughout your career. So yeah, that's my general overview. And I just had a couple pictures, but honestly, it's fine. It's not a big deal. So if there are any questions at this point, I also have a list of like the classes that I think are currently under the nanosystems concentration. So I can maybe answer a couple questions on them. I'm not going to be as good as the advisor on giving you any specific advice, but maybe if you have a question on a class and what it covers, maybe I can answer a little bit more, or maybe how it's related in the future. But yeah. Does anyone have any questions? Oh, silence
I
in the
guess
room.
to that while we're waiting on questions, if you
Sure.
would like, I can pull up the degree plan and you can kind of walk through some of the classes you took and maybe tell us a little bit about them.
Sure.
So cool beans. Let me do that really quick.
No
Yeah, I
worries.
do apologize. I did get sidetracked, I will say,
No worries. I
doing
actually
school.
do
So
have, I think like, yeah, I actually do have, I guess, the classes that are listed under the concentration that I could pull off the website. But
here, I
I
found the
can.
degree plan.
Oh, you did? Okay,
Yeah,
cool.
yeah, yeah. Let me share my screen really quick. And thank you, Nancy. And I believe I saw Doug on here too. Thank you both for coming and presenting to our students.
Hi, Doug.
Hello.
I remember you, Doug, from IAB, like one of the IAB meetings, but back when I was a student. So Doug's been around forever.
Well, I hope it was a pleasant memory.
Yeah, I'm sure it was just fine. I just vaguely remember Doug. It was one of those times I may have been talking to Dr. Fritz and it was like, what? Oh, look, it's Doug. But yeah.
All right. So I have it pulled up. And
Sure.
yeah, I have some good memories of Doug too, so I could second that. So I have it pulled up. I hope you guys can see it. And so I guess we
Can
can
see.
start with just the nanosystems required stuff.
Sure. So I think the requirement is that you have to select 2 to 3 classes out of just the concentration area, and nanosystems requires 3, if I read that correctly
Yeah, so you
somewhere.
have you have these that you have to take. These are required, and then you go on to the next page and
Oh, and
select
choose
two
3
now.
more.
It's select two now.
Okay.
Yeah. So if you want to go over some of the required classes just for a little bit, just because I
Yeah.
guess if you do nano, you kind of have to do these, I guess.
Yeah, and actually, I I do say it's a little difficult with some of these classes because they're a little less uh, intuitive when you're in the classroom, and so I don't know if there's been kind of more tours involvement more recently, but essentially when you go into a nanosystems concentration, you're like I said, you're kind of focusing in on what are the test equipment? What's the manufacturing equipment? What is the manufacturing process for a lot of these materials? So Intro to Nanotechnology is that very first class, which just says, hey, by the way, you can make devices that are really small. And device can be electronic, which is an electrical focus area, obviously, in the case of these classes. But there's also a lot of interdisciplinary work with biomedical, with chemical, with even mechanical, because you can have MEMS devices versus biological reactants or whatever might be the case. So this is just kind of a blanket overview of here's the entire industry. Um, And it's crazy because nanotechnology has been around literally since like 500 BC. So like we've had materials that are reactant in a chemical way, or in a physical like photovoltaic way, um, uh, since a long time ago. But moving forward, that kind of turns into, hey, what is a nanomaterials engineering aspect? Nanomaterials is more focused in the actual material properties, crystalline structures, yeah, what builds up a material that would make for a good uh, type of chemical interaction between two materials. This actually is actually pretty relevant because a lot of electronics, you specifically have to think of what are going to be the failure modes, especially in the space industry, aerospace industry. You want to think of like, oh, it's going to have tin whiskers on my antennas, etc. So it is relevant. It's not usually in industry, you don't really go so in depth of what's the wavelength of these two particles. You don't do that in industry, but at the same time, it is interesting to note a lot of, well, sorry, you don't do that in electrical design directly. But once you get into kind of the semiconductors and evaluating failure modes, like I said, and doing failure analysis or actual materials processing, what kind of manufacturing process is going to make those failures or could lead to those failures. That's what you're kind of directly applying that for. Design fabrication of nanoscale devices. This one's a little bit more, I had Dr. Bronkovic for this class, and it was actually pretty great with him because he was very engaging, had a lot of experience in the industry for being able to address just, here are a bunch of devices. Here's kind of how you consider to design them, and would actually take you into the lab, especially as an undergrad. He would basically put you in his lab, and you would work through a report and problem with his lab folks. And then, yeah, and then I kind of skipped solid state devices just because that's actually applicable. And it's an interesting course no matter which concentration you're interested in going with. But it's essentially from an electronics only perspective, because keep in mind the other three are all interdisciplinary, and you can actually find a chemical engineering or mechanical engineering log of the other three classes. But physical principles of solid state is actually an EE-led course, so it's from specifically to the department. And that one combines or bridges, so to say, electronics design and literally looking into what are the material structures for different types of transistors, BJT, yeah, any one of the transistors. So yeah, so that's kind of an overview of the core classes. And then I just took a bunch of random other ones. But yeah, so one of the classes that I loved taking was power electronics and electronic drives, with oh my gosh, his name is blanking on me right now. Oh my gosh, I loved him. Ah, I
I
can't
think
remember his name.
when I had that class, I took a guy named Gokder.
Oh no, that's
Uh,
not the professor I had. Ah, I can't think of his name right now. Oh my gosh. Well, anyway, I took power and electronics devices, and I loved my professor when I took him, and now I'm heartbroken that I can't remember his name. um, that was a really cool class. It's actually been super applicable, especially in avionics, because you're dealing with low power applications, mostly DC, not as many transient responses, not three phase. Uh, so yeah, it's just been useful. I actually highly recommend that class no matter where you go, especially if you want to do device electronics versus like power grid. But yeah, and then I did antenna engineering. Really useful for where I've gone. And that was actually a class that I specifically took right before I graduated because I knew I was going to be working in an RF world. So that one not as directly applicable to nanosystems, but essentially with any RF or microwave, it's kind of more of an envisionment of like, here's electromagnetics, here's the types of designs you want to make, and kind of the bridge between, again, I also know how you build these kinds of electronics. How would you go across around building them? And then here's the electronics theory behind them. So essentially, I would actually kind of pick kind of a bubble of, hey, I kind of want to focus on this realm of things. If I was doing this again, I'd really recommend doing that and doing applied electricity and magnetism and like microwave and antenna engineering is kind of one combination of classes to help you kind of get some depth into those classes. Circuits and systems was a pretty useful class actually. And then I did not take I actually did not do the nano engineering research, partially because I had a separate research opportunity. So yeah, I didn't do that one. Yeah, other than that, yeah, my general recommendation is kind of group them and then kind of stick to that group just because nanosystems is one that gives you so much broad overview across the industry that it just helps to combine them into kind of a smaller group and smaller band consistency. I guess I'll put it that way. But yeah, and I think I hit my 320 mark, so I don't want to go over Doug.
I think you and Doug are kind of back to back, so I think you guys both together share kind of the full hour. So
Got it. Oh, then in that case, I don't know if you had any input, Doug.
No, I think it was a good overview based on what you do. I think it's hard to talk about nanosystems in specific terms because it's so broad. Nanosystems and nanotechnology is just everywhere.
Oh
And
yeah.
so you kind of have to know what specialty you're interested in before you can advise people of how to prepare themselves for it. But there are certain basics, though, that you went over that you want to do no matter what. You want to do some solid state, no matter which direction you take. And you want to do, some fundamentals and circuits, no matter where you go. So there are certain things that cut across all of them. But then after that, it depends on whether you're going to be in biomedicine or you're going to be in agriculture or textiles or bioengineering or medicine, so it all depends where you take it as to how you want to prepare yourself.
I definitely agree with you, Doug. Yeah. And as far as, I guess, any recommendation that I thought of ahead of time specifically, it would just be, I guess, if you think of it as a narrow pathway, I guess, if you want to take nanosystems and go the fabrication route and go all the way, then definitely look up the foundries, get familiar with what those manufacturing chip locations are. And then, like Doug said, get a firm background in a lot of your electronics design and kind of focus in on that. Otherwise, if you want to kind of focus in on EM, a lot of photonics, like a lot of universities are doing photonics research, light wave applications, things like that. So definitely a solid path that way as well. So I'm curious if there are any questions around here.
Well, I guess as we're waiting for questions again, I'll go ahead and ask one myself. Is, you kind of have, I witness, you're a little more out from whenever I graduated, although I graduated at a different concentration. But, what are some things in your degree plan that you kind of, or as far as what you learned in classes that you either used, or you use now, or you have used?
Um, let's see, something specific that I have used from my classes. I would probably say it's actually kind of crazy because I currently am working on a design program, design phase program, and that's been a really awesome opportunity to basically do circuits design again, and some of it pretty basic, others not so basic, and I kind of rely on the older, the more experienced electricals to help me out with some of those designs. So it's been really cool to be able to actually apply like the math and the resist and the logic, circuit logic that you can. A lot more common though is doing a lot more software work. And I just say it's more common because honestly, a lot of the embedded design, a lot of the system on a chip or FPGA, a lot of that stuff. Although you kind of do have to know VLSI and try to do FPGA stuff. I'm not as familiar with it, obviously, but it's just kind of, it leans in more software oriented. So definitely don't forget a lot of those microprocessor classes because those will get you um, pretty far along. Yeah, kind of depending on if you're working on a development program or a sustainment program, from a sustainment perspective, or if you're kind of into production, it's actually really beneficial to know just the manufacturing processes, what the vendors are going through, what kinds of failure analysis, again, that you're going to be working on. So yeah, that would kind of be my 2 cents. I don't know if Doug, you had a different experience.
No, again, it kind of goes, what direction are you heading in? You can certainly go in the circuit design direction, or you could go in the fabrication direction, or you could go in the system direction. So it all depends on where you want to head. I guess if you were to say what generalizes, I would say get a good foundation in math, get a good foundation in electricity and magnetism and circuit design, because those are the kinds of the things that kind of cut across everything. It's almost impossible to take too much math because no matter what you do, you're going to need to know some math. And but there's not a lot of room in your curriculum anyway. But anyway, that helps if you have a grounding in the fundamentals. And one of the things I was going to say in my presentation is systems have gotten really complex, and they're getting more and more complex as we go. And what that means is that you don't have all the knowledge that you need in a system, but you have to specialize in something that you're going to do well. And when you get in that kind of a situation, no matter how much technology changes, what's not going to change is Kirchhoff circuit laws or Ohm's law or Maxwell's equations or the laws of thermodynamics. Those are not going to change no matter how the technology changes. They're going to be the same. They're going to be the foundation for all of it. And so the better you are at those things, the easier it's going to be for you to transition from one technology to the other. And I can tell you it's changing very fast. Technology changes very fast.
So here's another one. There's a question in the chat, and I guess it's kind of similar to, I guess, the question I asked, but I also kind of want to hear from both of you guys, see what y'all's input in this. What's the day in the life of a nanosystems engineer?
Well, I
You
think
want
you're
to
going to
take?
get two different answers because I spent most of my career in kind of a management role. And that's a little bit different than, let's say, the everyday engineer's role. But in a management role, basically you're communicating with your team, which is international. And so as a manager, you're essentially on 24/7 because there are different time zones all over the world. So there's no time when the project is not progressing somewhere in the world, and they don't have the same holidays that you have. So just because it's Christmas for you, it may not be Christmas for somebody in Asia. And so you have to be ready to respond at any time of the night and day, 7 days of the week. And you have to be good at putting out fires because, when I was driving to work on Monday morning, I would say, okay, what is the crisis going to be this week that we're going to have to deal with? And I won't find out till I get to my office. Nowadays, of course, we work from home, but before I retired, I worked in an office building. And so the question is, okay, what decisions have to be made? What are the problems? How do we get around the problems? Who's the best person to help with the solution, et cetera? So that would be a very different experience than, let's say, Nancy would, who may be at the sort of a junior level. Her workday would look quite a bit different than mine did.
For sure. I want to say I would agree that it's actually been a lot more management or product oriented as far as product management, but at the same time, it's a lot more of, hey, got to get this task done and work forward with it. And I actually have to transition rooms, so I'm going to be silent for a few minutes, just FYI. I don't know if Doug, you wanted to take over with your half of the presentation.
Yeah, whenever you guys are ready.
Yeah, go for it. Might
Okay,
opportune time as ever.
Can you allow me to share?
I believe you should be allowed. Oh, there it goes. All right. Now you can. Sorry about that.
Okay, tell me if you can see this.
I can see it. It says nanotechnology, and it's got a lot of my favorite color in it.
Yes, the color of money, right?
Yeah.
So let me see if I can
it does happen to be that too.
Let's see. Let me go to the slideshow. Can you still see it?
Yes, sir.
Okay, so what I did was I spent 5 years teaching physics and math in high school. And then I spent 5 years at the university level teaching physics and pre-engineering. And then I spent about 35 years at Texas Instruments doing integrated circuit technology. And I think what I mostly did at TI was to lead development projects that would develop the technology that's used to make integrated circuits. And so basically what you need, the kind of knowledge you need to do that kind of work is first of all, you need to have some knowledge of device physics. You have to know the physics of how the devices work and what you can do and what you can't do. You probably also need to know how the devices are fabricated. What are the fabrication steps? You have to know something about lithography and about wet chemical etches and wet chemical cleans and plasma etching and plasma depositions, et cetera, which you would normally take, let's say, in a fabrication course. So you have to know all of those things, and you have to know how this all comes together to produce a transistor that has the right characteristics that you're looking for. And so that's what I did for a long time. You probably have some of the devices my team developed. If you have, for example, Sirius XM radio, or if you have a MacBook Pro or a MacBook Air, or if you have a modern automobile with anti-locking brakes or with electronic stabilization, or with a dashboard that has information and entertainment on it, then very likely you are not more than 3 feet away from one of the chips that my team designed, developed, produced, and sold. So that's what I did. Now, if you're talking about nanotechnology in general, and I was only in the electronics part of that, designing transistors and technology. But as I was saying previously, nanotechnology encompasses a huge variety of things. And agriculture, medicine, pharmaceuticals, electronics, textiles, chemicals, food, material science, aeronautics, et cetera, et cetera, et cetera. So it's a huge field. At the University of Houston, I think what the emphasis has been is on one part of that, and that is with nanobiophotonics and with nanomaterials and nanofabrication. That's the activity that's taking place at the University of Houston. And I'm not familiar enough with the courses to tell you which ones of those you should take, but that's how they fall in. And then on this scale in the middle, you can see the size of, you can see with a nanoscale how it fits into the universe that you may know. Technically, nanotechnology has to do with sizes that are between 1 and 100 nanometers. And you might be surprised to know that we've been doing nanotechnology at the integrated circuits level for probably 20 years, because the 90 nanometer node was first put into production in 2003. And today we're now at the 5 nanometer node. And so that's still within that scale from 100 to 1. And the node refers to the smallest geometry that you could pattern and etch on a circuit. So 90 nanometer meant that's as small as you can make it at that technology node. And now we're down to 5 nanometers. And the scale of integration is just absolutely mind-boggling, because you can now buy an NVIDIA integrated circuit, which has 18 billion transistors. That's mind-blowing, that you can think of what you could do with a circuit that has 18 billion transistors, probably 4 billion gates in it. So we're still in the nanotechnology mode in electronics, and we've been that way since 2003. And in the foreseeable future, there's still more shrinking or scaling to do in the next maybe decade or so. After that, I don't know what happens, because now you're getting to the molecular level, and you're not at the level of a film or a crystal anymore. You're down to single molecules. So there is tremendous investment in nanotechnology. So it's a good field to be in. The compound annual growth rate is estimated to be over 14% a year. That's a tremendous growth rate. And in 5 years, the investment is going to be like 121 billion. So when you get that kind of investment in a technology, that means that technology is fast growing. And that means for students, that means there are going to be jobs in nanotechnology because of that tremendous growth rate. So that kind of is good news and bad news. And the reason that it's good news is because, the appetite for technical knowledge, it goes on unabated. And it means that the markets are fast changing. And it means that the systems are going to be very complex. And because it's very complex, no one engineers know the whole system. So that means there's going to be more specialization that's going to be required, even though at the same time, you really need to understand the whole system. The bad news is that there's going to be a diminishing engineering knowledge half-life. What I'm told for the people who study this is that the engineering half-life is between 2 and 5 years, depending on what specific technology you're in. So if you're in nanotechnology, so it's so fast growing that you're probably closer to the 2 years than the 5 years. And in case you don't know what half-life is, it's a term borrowed from nuclear engineering. The half-life of an isotope means that That's the span of time when its radioactivity is diminished by 50%. So if your engineering knowledge half-life is, let's say, 3 years, that means that in 3 years, half of what you learned in college is obsolete. And that's a depressing thought, right? If you spent 4 or 5 years trying to get an engineering education and then faced with the reality that in 2 or 3 years, half of it won't be useful anymore because they're obsolete, that's kind of depressing. By the way, this is not only happening in nanotechnology, it's happening in a lot of other places as well, like in robotics, cybersecurity, and in artificial intelligence, in all sorts of technology fields. So it's not just nanotechnology, but it's particularly so in nanotechnology. So how does a student deal with this? How do you prepare yourself for going into an environment where you become obsolete in 2 or 3 years? Well, not totally obsolete, just half obsolete in 2 or 3 years. Well, is what we were talking about earlier. The fundamentals are not going to change. The laws of thermodynamics are not going to change. You know, the circuit laws and Ohm's law and Maxwell's equations are not going to change. No matter how the technology change, what will happen is how it's applied will change. And that's where the innovation will take place. But Maxwell's equations will still be Maxwell's equations. Ohm's law will still be Ohm's law. So get a good grounding in fundamentals and good grounding in math. And that's one way of dealing with a fast changing technology environment. And you have to become a lifelong learner. You know, as I said to you before, I spent 45 years in a career, and the last year before I retired, I was still learning things that I needed to know because there was some topic that I needed to understand better in order to solve a problem. So I had to go learn that particular topic. And there was more than one time when I said to myself, you know, I wish I'd have paid more attention when we covered this particular chapter in my solid state course, because now I can understand how I really need to know this in order to solve this problem. So you have to become a lifelong learner in technology. Otherwise, you yourself will become obsolete in just a short period of time. And one of the ways you can become a lifelong learner is develop a technical network of people that you talk to and you know. I had no hesitancy ever of calling somebody and say, hey, you're the best person I know that knows antennas. I'm seeing this. What's your thoughts about it? You know, I had no hesitancy in doing that. And that's one of the ways that you stay up to date is you develop a network of experts that know more than you know and that you can talk to and they can talk to you about what you know. So it's a good investment to develop a network. It's a good investment to find mentors who are good at the kinds of things that you want to do. You know, my mentors were program managers and project leaders because that's what I did. Is I led process development teams and technology development teams to produce technologies and develop teaming skills, because everything is so complex these days that you have to work in a team of people that know the whole system. So you may have to know antennas or displays or signals, or you may have to know telephony, or you may have to know RF. You may have to know a lot of different things in order for the system to work, and you're not an expert in all of them. You know, so if you're an effective worker in a team, you will be a strong contributor. If you have a grounding in fundamentals, you will be a strong contributor. If you learn as you go, you will be a strong contributor. So that is, you know, to me, how you prepare yourself to go into a world where the technology is just changing at a lightning speed. Now, talking about networks, you have access to a network of very experienced people in the industry advisory board. So these are the people, there are 32 members in our advisory board. These are the people who are on the board, and you can contact at any time. That you can say, okay, do you have any job openings? Do you have any internships? What can you tell me about this? Because I'm having a problem with it and I can't solve it. And you're from NASA, so you should be able to help me. Or, you're from HP, or you're from, TI or MD Anderson, or you're with Omron. And these are people who have, I would say, between 400 and 500 years of experience in the industry, solving real problems. And there's one in here, Colin, that you will recognize, I think. The way you
Yes,
contact them
very
is
much
through
so.
the industry. If you look at that website address at the bottom, it's just in the people directory. There's one that's called Industry Advisory Board. If you go there, you can have access to all of these people that are on the board, who can be a resource for you that you can use to develop your technical network, which I just described for you as something that you really want to be able to do. And then lastly, and I'm going to end with this, one of the things that this industry advisory board did is that it told the department, the ECE department, look, here are the skills and knowledges that we want to see for graduates coming out of the university. Now, I'm not going to necessarily tell you how to do this, but if you can produce students that have these skills and knowledge, they would be eminently hireable. This is what we look for. And if you're smart and you're doing job interviews, what you do is you go look at this, and because this is what the people who interview you are looking for. They're looking for these kinds of things. And if you can describe to them, how you have these skills or how you have this knowledge because of what you've done, then you have an advantage over the other people that are interviewing, because they're telling you directly what they want from you. So you kind of have, in a way, a cheat sheet here that says, look, if you can do these things, matter of fact, if you can do all of these things, I'm going to hire you right now on the spot. And so these are the things that they want. This is what they've told the department that they want from students. And this is what you as students can use. And you find this, again, at the same website. And you see it up at the top of the page here at that industry advisory board website. It's under the name of skills and knowledge useful in the workforce. Okay, so that's what I have to say to you. It kind of echoes some of the things that Nancy was telling you, and that I was saying before as well. And so let me see what your comments are or your questions, and I'll see if I can answer them. No, I think I put everybody to sleep.
I'm
Don't worry,
still
it
awake.
was me first, Doug.
We have such a rowdy audience today.
Yeah, I know. You need
It
to get
happens.
control of these guys and ladies, Colin.
Yeah, no kidding.
Well, Nancy invited me to comment, and Nancy, I'm going to invite you to comment about what I said.
Yeah, this is actually really interesting, mainly because from the perspective of actually being able to lay out what skills are relevant. I'm really interested in these slides. But I would definitely reaffirm the concept of getting a base knowledge of your math skills. It seems really irrelevant. Maybe as you're going through school and you're thinking, oh, but my first job, will I really be using this? It's, I guess my experience has been, even if you don't use it on your first job, you may use it on your second or your third, right? So it's just something that you continuously use. And it's good to have that fundamental knowledge moving forward, because you never know when it'll pop up, whether it's in 5 years after your graduation or whether it's in 50. So math is fun, and it's the best part of engineering, let's face it.
Sure. So nowadays, if you want to be in nanotechnology, and let's say you want to do design, circuit design at the integrated circuit level, you really don't need to have an intimate knowledge of device physics to do that, because now when you do ULSI scale design, you use ECAD tools, and the design is done at the register level. So what you're working at is in the digital logic, and how do you put registers together to produce a certain functionality. So those kinds of skills have more to do with, are you familiar with ECAD tools? Do you know digital logic? Now, if you're in analog design, that's kind of a different skill, because that's more maybe craftsman style, and there's less ECAD and automation that's done in automotive design. I'm sorry, automated design than you do in digital. And the reason for that is because it doesn't scale as fast. There are certain disadvantages to scaling analog too small, because you rely on a lot of matching properties. You know, matching transistors are really important, and matching capacitors are really important if you're building a differential amplifier. If you have a mismatch, then it's not going to work very well. And so you need to have more hands-on skill and more knowledge and skill with layout than you actually do with the circuit itself. And so there's a different skill set involved in analog design than digital design. So what do you do when there's like a mixed signal design where you're combining both digital and analog? Then you have to have some knowledge of both when you're doing that. And that's not necessarily at the transistor level. So what I did though was to provide the technology to my design team for them to design with. And so this is how the transistor was designed. This is how a capacitor was designed. This is how a resistor is designed, et cetera, et cetera.
And I would actually just jump on that, Doug, just for a second, because it's actually very interesting, the way that ICs are now getting more and more capable, where you can buy smaller and smaller ICs. It's kind of linking a bunch of ICs together. So it may not be as obvious as, you know, in analog design, you actually, you know, see the transistor, you see what it's supposed to do. But linking everything together through ICs also does something similar, or you end up getting kind of a culmination of designs in that way. So it's interesting because you're getting more of a systems interpretation of each one of the devices at smaller and smaller scales.
Well, yeah, that's the point of integration is to put more and more of it on the chip. So the more you can integrate onto the chip, theoretically, the lower the system cost is, because now you don't need to have 5 chips. You can just do 1 chip. And that 1 chip is less expensive most of the time than the other 5. Although what I've seen lately is, like, for example, NVIDIA, they basically have actually de-integrated. They used to embed the flash in their chips, but their chips got to be so big. Like I said, 18 billion transistors is just absolutely mind-boggling that you can do that. So what they did is they took the memory off the chip, and now they put them in what's called multi-chip modules. So they lay them out so in sort of chiplets, where the memory is separate from the logic, not the cache memory, but the non-volatile memory, you know, like flash, for example. They integrate it off the chip. And so when you go to retrieve information, you have to go off the chip, retrieve some data, and come back onto the chip. That tends to slow things down. But sometimes it is more cost effective to do that, because when you build a huge integrated circuit with 18 billion transistors, the yield of that chip is very low. So it can get kind of expensive when the chip gets that big. It actually might be cheaper in certain circumstances to actually de-integrate parts of the circuit to other chips, which you can put in the same package. Well, I thought I'd have more questions, but I see David has joined. Hello, David.
Yeah, I kind of
I
was
think I just
hoping to
kind
hear
of
some good
buffaloed
questions too.
everybody, David. They don't have any questions.
I was really hoping to hear some good questions myself. I always know if I'm learning, I have a question. That's always what I found.
Well, let me
Did
end by saying, let me go back to the point I was making before. Given the environment where everything is changing so fast, becoming more complex than it's ever been before, these are the things that I hope you take away from, because I can't really tell you take this course and take that course because I don't know the curriculum well enough to tell you to do that. But I would like to reiterate this. These are the things that I think you want to remember. Get a good grounding in fundamentals. Those aren't going to change. No matter how fast the technology changes or how complex it's going to be, at its root, it's always going to be based upon the fundamental laws of physics and engineering. As I said, Maxwell's equations are not going to change. They're going to be the same no matter what the technology is. Become a lifelong learner. If you don't keep learning, your degree is not the end of your learning. Your degree better be the beginning of learning, because everything is going to change very fast, and you have to be able to keep up with it. And that's more than just taking courses. That's just learning where to go get the information that you need. One place to get it is in your technical network. Invest in your technical network. It's a good investment because it can help you in your career if you know the best people in certain technology fields and you have the ability to communicate with them because you've taken some time to develop a network. Then you'll be in good stead. Find mentors and develop teaming skills because technology is too complicated these days for any one person to do it. I mean, just take a cell phone. Is there any one engineer that could really put together a cell phone? Yeah, I mean, it has, materials, properties, packaging, antennas, displays, telephones, RF, Bluetooth. I mean, it just goes on and on and on and on, NFC, et cetera. So who's an expert in all of those things? There's probably no one engineer that knows all of those things. And yet a cell phone is now ubiquitous, right? I mean, it's unheard of for a technical person not to have a cell phone, which is a computer and a phone and a communication device, and it's all of those things. And there's no one engineer that knows all of it. And so that's just one example of what I'm talking about. That's the way we are today in modern engineering. And that's the environment that you're going to go into. And so you have to learn how to function in that kind of environment. So I know I'm repeating myself, but I think these are the key points that I wanted to leave you with.
All right. Well, thank you very much, Doug. I guess, are there any more questions?
I don't know, David, do you have any comments? You caught the tail end of this.
I've heard parts of your presentation before, Doug, and my general comment would be I wish I had seen this when I was a graduating senior, because I had to learn a lot of these things the hard way, and some of these things didn't really click with me until I saw Doug talk about them. And so take this stuff to heart. This is a long career worth of wisdom distilled down into a PowerPoint, and I can promise you'll stumble and come across these topics throughout your career.
Okay, so Colin, I guess that's all I had to say.
No, I think that was a great deal of information. I know for me, I've definitely learned something. It looks like they're thanking you for your presentation in the chat. So,
Okay. Thank you,
all right.
Colin.
Well, no problem. Thank you, Doug, and thank you, Nancy, for coming and presenting on nanotechnology. We really appreciate that. And you feel free to stick around if y'all like to stick around. If y'all have work to do, we understand that as well.
Yeah, have a good one, guys.
Later, Nancy.
Thank you for the invite and happy to do it.
No problem. Maybe next time it'll go a little smoother at the intro.
Not a problem.
All right. All right. Well, I guess with that, it is nearing 4 o'clock. So I guess we'll go ahead and jump in. As Doug pointed out, we have our very own David Hanson over here. And I guess, David, I will say